Okay, so let's start getting after it with this UART programming. So in the last video, we talked a little bit about just how to write a real simple program to test to make sure that the our computer was, executing code correctly. And here, what we're going to do is we're going to actually write a real program that actually prints stuff to the UART. So I've copied quite a bit of the stuff from that last program into this 68681 test program here. So I got the vector table, as you can see, which starts at address 0 and contains these two important vectors, the stack and the start. And then the rest of the vector table is pretty much just populated with this dummy handler thing. So this is a exception vector, which is never going to be actually executed, but we put it in there anyway. Okay. So here's my start program is pretty sparse right now, right? I just have a initialization of the stack pointer, and I have my dummy handler here, which is just doing a return from exception. So the three things, I kind of need like three functions in this program to print and receive characters from the UART. Okay, the first one I need here is going to be an initialization function. Which is going to be basically initializing in software the 68681 UART. So we'll make a function for that, which is just going to initialize our UART. And this is going to be called at the beginning of our program, right after the computer first boots up. We're going to initialize the UART in software, and this is going to configure the things like the baud rate of the UART, and other data transmission properties. Okay. The second function I need is a function to print a character to the UART. Okay, so we're just going to send one character to the UART. We'll call this put C. Okay, this is going to print a single character. And then, of course, we will also need a get character function as well. Okay, so these are the three mandatory functions that we're going to need to run the UART. And possibly we may also want to implement a third or a fourth function called putS, which is going to print a full string to the UART by just sequentially calling putC over and over again. Okay, but let's start with this initialization function, the init 68681, and see how we do. Okay, so in order to write this function, we're going to need to look at the data sheet of the 68681. So I have that pulled up behind us here, and I have sort of scrolled down to page 8. This is the Philips semiconductor data sheet. There's a couple of data sheets out there that I found on Google. This one is a little bit more useful than the other one I found. So this is the one I've been using to run all my tests. So I would download this data sheet and read through it. It tells you, the pin configuration of what your UART is going to look like. If you have the DIP or the PLCC package, it has a pretty descriptive explanation of what every pin does. But since we've already wired up the hardware, we don't really need any of this stuff right now. So what I'm going to do is I'm going to scroll down to the register definitions down here, which is going to tell us how to use this UART in software. And this is a little bit confusing. So let me just kind of go through it slowly here. So basically, this UART has a total of 16 registers in it, and each one of those registers is mapped to a memory location on our homebrew computer's memory map. Okay, so just like the RAM and the flash were mapped to different memory addresses, we can also use the same memory bus that we use to talk to the RAM and the flash to talk to this UART. Okay, and we're only going to run 4 address lines to this thing, A0 through A3. They're labeled differently here. We're running A0, A1, A2, and A3 to the UART, right? Okay, so each one of these registers, each one of these addresses, I should say, that the UART responds to, can have a different register in it. And you'll notice here that depending on whether you're reading or writing to the UART, it may have a different, sort of like a different meaning, right? So for example, address 1, if we have the address pin 0001 and we're reading from the UART, we're going to read from the status register. But if we're writing to that same address, we're going to write to the clock select register A. Okay, so so we can't actually read the value of the CSRA. Because if we read to this address where this thing is located, then we're going to read the status register at that location. And I think this was done basically to make the most out of 4 address lines, right? So if we had 5 address lines for this chip, then we probably could have read and written to all of these registers. But the registers that you can write from, for the most part, the registers that you can write to, for the most part, you cannot read their value back. And the registers that you read from generally cannot be written to. There's a few exceptions, but that's the general rule. Okay, so this can be a little bit it can be a little confusing when you're trying to set this thing up for the first time. If you have some kind of a configuration problem with your UART, it's very difficult to find the problem because you can't actually read back the values that you've written to your to your registers basically. Okay, and to confirm that they're correct. Okay. So that's the first confusing thing about this UART. The second confusing thing about this UART is that if we zoom in on address 0 here, mode register A, what you'll see is that mode register A lives at address 0, but there's actually 2 registers associated with this thing here. It's MR1A and MR2A. Okay, so this is the same address which can be used to set and read the value of 2 different registers. So basically the way this thing works is when the chip is reset, we can, there's like a pointer that points to mode register 1A. Okay, so this is like it tells us what the mode of operation for UART A is on this chip. There's 2 UARTs on this chip, A and B, right? And so we're going to be using UART A. And so if we want to control the parameters of UART A, we're going to write to MR1A and MR2A, right? And so in order to write to mode register A, we're going to start out by writing to MR1A. There's a pointer that points to MR1A when this thing is reset. And then as soon as we write one value to MR1A, that pointer is incremented to point to MR2A. So then we're going to then write to MR2A to set whatever configuration settings we need to set in there. And then the pointer will be reset back to MR1A. So basically every time you write to address 0 on this chip, that pointer is going to flip back and forth between MR1A and MR2A. Okay, so there's these 2 control registers here that are mapped to the same address. So this is really confusing. Okay. So anyway, I'll explain how to deal with that in a few minutes. Okay. So, and then I think there's one more confusing thing about this chip, and that is that basically maybe not almost all, I was going to say almost all of the configuration registers, but many of the configuration registers have a delay in response when you write to them. So what that means is, I'm sorry, that's not right. Okay, so the third confusing thing here is that the CRA register, which is located at address 2, CRA, this register has a delay in response when you write to it. So basically when we write to this register, we're going to be sending a command to the UART. And every time we send a command, we have to wait for a little while after we send that command for that command to be processed. So we can't just send a command to CRA and then immediately afterwards send a second command. Okay, we have to send the first command and then wait for a few cycles, and then after we're done waiting, then we can send the second command. Okay, So that's sort of like the last confusing thing about this UART. Okay, so let me go through the order of operations here that we need to to configure this thing. Okay, so in the initialization program here, so I'm going to let me just comment this a little bit. Okay, so we're only going to be using UART here because that's the only one we wired up on our board. So the order of operations here for initializing this thing is that we are going to reset everything, right? We need to reset all of the functional units on the UART. So we need to reset the receiver, the transmitter, the error status, and the mode register pointer. That's the pointer that points to MR1A or MR2A. Okay, so those are the 4 things we need to reset. And actually, every time we perform one of these operations, after we reset the receiver, we need to wait for a few clock cycles before we send the next command to reset the transmitter. Okay. If we don't wait a few cycles in between sending these commands to the CRA, then we will not be able. The command will not be. It won't take basically. All right. So after we're done resetting all the functional units, we need to configure the number of data bits in parity by writing to, I believe it is the mode register. Let me see here. Yeah, that's the mode register. Okay. Then we're going to configure the flow control and the stop bits in the mode register. All right, so the first one is going to be MR1A, and the second one is going to be MR2A. Okay. After we've configured that, we're going to configure the baud rate. That's going to be in the baud rate generator register, I believe. Okay, and after we've configured the baud rate, we're going to enable in the receiver and the transmitter in the CRA. Okay, and then once we've done that, we are going to disable our interrupts. Well, wait, no. I'm going to set, okay, it looks like we need to set ACR of 7 equal to 0. Then we're going to disable the interrupts. And that's all we need to do there. So this is a 7-step process. Okay. Okay. So first of all, let's take a look at this at the CRA. This first step is going to be done in the CRA. So let's take a peek at the CRA and see what that looks like. So if I look here, I can see that my CRA lives at address 0010 on the UART, right? This is the base address. This is like the base address of the UART plus 0010. That's the CRA, okay? But we've mapped our UART to address 100,000 hex, right? If you remember from the memory map discussion, basically our UART lives at address 100,000 hex, right? So what I've done here, and I'll post this on the website for this project, is I basically configured all of the addresses for each one of the registers on this UART, right? So we have the MRA lives at address 100,000, the SRA lives at 100,001, and so on. The CRA lives at 100,002. Okay, this is the command register. Okay, so basically you can see that the CRA is here. So let's go down, we'll scroll down a little bit and look to see what the CRA bits mean. Okay, so we can see here we have basically we have a bit 7, which is unused, and then we have these 3 bits, 6, 5, and 4, which are these miscellaneous commands in the CRA. These are the things that we're going to be sending first. We're going to be sending 3 commands to this thing, 3 or 4 commands. And then we have bits, the low order nibble, 3 down to 0. This is enabling and disabling the different functional units on this UART. Okay, so we need to look at these miscellaneous commands to see what's available to us. Okay, so let's scroll down here to see where the commands are. Here we go. Here we go. Channel A command register. Here are our commands. Okay. So the first command we want to send to this thing is going to be to reset the receiver. Okay. So that the code for that command is 010. Okay. So we're going to send command 010 to the CRA, and that's going to be in bits 6 down to 4 of the CRA. Okay. So let's do that real quick. Okay. All right, let me scroll down here. All right, so in my initialization code, the first thing I'm going to do is I'm going to get the address of CRA into I believe it's called Uart CRA. Let me just check here. Uart CRA. We're going to get that in register A0. Okay, so we have a pointer to the Uart CRA. And now we're going to move the command for resetting the receiver into this register here. Okay, so basically this command is going to be 0 everywhere except in bit 6 down to 4. Bit 6 down to 4 are going to have 0, 1, 0 in them. Okay, so bit 7 is going to have a 0. Let me just comment this real quick here. 7 is going to have a 0. 6 down to 4 are going to be 0, 1, 0. And then all the rest of the bits are going to be 0. Okay, so this is the byte that's going to get written to the CRA in order to reset the receiver, right? This has zeros everywhere except bits 6 down to 4 or 0, 1, 0, which is this command to reset the receiver, right? And so this is the binary version of that. The hex version of that is equal to hex 20, okay? So we'll say move.b hex 20 to A0. Okay, so this is going to reset the receiver. Okay, and now, as I said before, we're going to wait for a few cycles here. You have to wait a few times. And then basically, after we're done waiting, then we can send the next command. Okay, so the next command is going to be to reset the transmitter. Okay, so the transmitter reset is going to be coded for by 011. Okay, it's similar to the reset, but it's going to be resetting the transmitter instead. So 011 in bits 6 down to 4. Let me go back to my assembly code here. So this is going to be, these 3 bits here are going to be 011, right? And then that's going to be in hexadecimal, that's going to be hex 30. Okay, so we're going to move hex 30 to the CRA, and that's going to reset the transmitter. And then we're going to wait again by running a bunch of no-ops. Good. Okay, then we need to reset the error status. Let's see here. Where's the error status reset? Right here, 100. So we'll reset the error status. Let me just copy all this code again. It's going to be the same. So this time we're going to be sending a 40, right? That's going to reset the error status. And then finally we're going to reset the mode register pointer, which is command 1. Okay, so that's going to be 1, 0 that we're going to send. Okay. Okay, so here we go. So now we have reset all of the functional units on this thing by writing these different commands to the Acr register, right, which is pointed to by A0. Okay, so now we're ready to start moving on to operation 2, which is going to be to configure the data bits and parity in mode register 1A. So let's look at mode register 1A. So we want 8 data bits and no parity. That's the standard. Configuration for these things. Okay. Okay. So we have here's our flow control. We have Rx RTS flow control. We want that to be no. Rx int select. We don't care about that because we're not using interrupts. Error mode is we can put that as a 0. So these three can be 0, 0, 0. Okay. Parity mode is going to be no parity. So that's going to be 1, 0. Okay. So let me just write this down here in our MR1A. I'll write it down in binary. So we said we're going to have 0 for bit 7, which is going to be RTS control, right? We're not going to use RTS control. Interrupt select, we don't care about that. We'll leave that as a 0. Error mode, we'll leave that as a 0. We don't care about that either. Hopefully we don't have any errors. And then our parity mode, we want that to be 1, 0, so no parity. Okay, so that's going to be 1, 0. And then parity type, we don't care about that, so we can make that a 0 also. And then bits per character, we want that to be 8, which is going to be 1, 1. Okay, so in hex, this is going to be the command that we're going to send to this thing is going to be 1, 3. Okay, so we're going to write the command. We're going to write that number 1, 3 to mode register 1A. Okay, so let's first get the address of mode register 1A into A0. All right, so this is going to be MRA, I believe. Let's go up and see what the name for this thing was. So we're going to have Uart MRA. And we're going to put that into A0. Okay, and then we're going to write the value 1, 3 to MRA. Okay, MR1A. Okay, so and after we perform this write operation, the mode register pointer will be changed to point to MR2A. Right, so then the next time we write to this address, MRA, instead of writing to MR1A, we're going to write to MR2A, which is going to control some other things, some other parameters of this of the Uart, right? So we're going to have this is MR2A here, right? So we have the channel mode, right? We want normal channel mode, which is going to be 0, 0. Okay. So that's going to be 0, 0 for normal mode. And then we want to have RTS control. We don't want transmit RTS control. We're going to put a 0 there. We're not going to have CTS control. We're going to put a 0 there. And then the stop bit links, we want 1 stop bit. So we're going to put 7 in the low order 4 bits. So that's going to be 0, 1, 1, 1. That's a 7. Right, so we're going to write the value 0, 7 to MR2A. Let's do that. There we go. Cool. Okay. All right, so just reminding us quickly here, this is setting up 8 data bits and no parity. And then this, and when we write to MR2A, we're going to set no flow control and 1 stop bit. And then we're done with the mode register. Okay, so now we need to set the baud rate register. Okay. Let's see here. Here we go. Here's the baud rate register. Okay. Wait, no, that's the clock select. Oh, here we go. Okay. Here's our baud rate register. Okay, so to set the baud rate, I think we have to set this SRA. Okay, so SRA is going to control the baud rate, which is going to be, so SRA lives at address clock. Oh, we need to write the clock select register, CSRA, excuse me. So it lives at address 1. So what we're going to do is we're going to set the clock select register A to basically what we want to do here is we want to have 19.2K baud. Okay, so we're going to set CSR. So our clock is 3.6864 megahertz, right? And so what we're going to do is we're going to set clock select register A to 1100, and we're going to set ACR of 7 to 1, and that's going to give us 19.2K baud. That's how we do that. Okay. And it is possible, they say here, to get rates up to 115.2K baud, but we won't mess with that. We'll just use 19.2. That's fine. So we need to set CSRA 7 down to 4 to 1100. Right, so let's go and look at CSRA. Look at the bit definition of that. Here we go. So this is the CSRA bit. Right, so we have two different clocks here for the receiver and for the transmitter. We want to set them both to be the same. Okay, so we want the clock select for the receiver to be the same as the clock select for the transmitter. And both of those, according to this table, should be 1100 in order to get 19.2K baud. Okay, so let's do that. So we'll get the address of CSRA into A0. Okay, and then we're gonna put the value 1100, which is C, in the upper nibble and the lower nibble of the CSRA. Okay, and then in addition to doing that, we also need to set the ACR bit 7 to be a 1. Excuse me. Yeah, ACR bit 7 is going to be a 1. Okay. I should have changed that there. Okay. So let's take a look at the ACR register to see what that thing does. This is the auxiliary control register, I believe it's what it's called. So this is bit 7 controls your baud rate generator select. So we're going to set that to a 1, and that's going to give us 19.2K baud. So let's do that real quick. Is it called ACR? Let me just check here real quick. These are ACR. Yeah. Okay. All right, and then we are going to put a 1 into bit 7. So that's going to be hex 80. All right. And then we're going to enable the transmitter and the receiver, right? And that's going to be done in CRA. Okay, so let's check CRA. Bit definition here. Enable the transmitter and enable the receiver. But set bits 0 and 2. Okay, so that's going to be 1, 0, 1. That's going to be 5. Right? Let's do that. Okay. So then we're going to enable the receiver and the transmitter that way. And now we are going to disable interrupts by writing to the interrupt mask register. We're going to write, we basically want to turn all of these interrupt sources off, right? So there's a bunch of different ways that the Uart can interrupt the microprocessor. We don't want interrupts on this program, so we're going to set all of these numbers, we're going to set all of these bits to 0 to make sure that all of our interrupts are turned off. Okay, so the interrupt mask register lives at this address here. Lives at address 100,005. So we're going to set address 100,005 to 0. Okay, good. And that is all we need to do. So this is basically the configuration for this Uart. So you know, it took me a long time. It took me a few hours to get this to work correctly. I had to really mess around with it. So I didn't just know all this stuff off of the top of my head. I was using a reference program that I wrote to make sure I get these numbers right when I explain them here. The biggest challenge of doing this, of course, is that there's all these little gotchas with this Uart, right? So every time you write to the CRA, you have to wait for a few cycles for that command to be latched internally, right? And then, of course, you have to make sure that you get your baud rate clock selection correct. So all that stuff took a long time to figure out, but I believe these are the correct values that need to be written to those registers in order to get the Uart to function at 19.2K baud. Okay, so that's how we're gonna. That's basically the gist of this setup program here, this initialization program. So what we can do here is we're going to call this initialization function as soon as we, right at the beginning of our program here. And then this is going. The first thing we're going to do is we're going to set up the stack pointer, and then we're going to branch to this initialization function here, which is going to set up our Uart. And this only needs to be done once at the beginning when we boot up, and then once it's initialized for the first time, then we're done. We don't need to initialize it again. Okay. So then, if you recall, there's two other functions that I really wanted to write here: putC and getC, and possibly putS. Okay. So let's do putC real quick. Okay. So putC, this is a function that takes one argument, and that's going to be an integer. Okay, that we're going to pass to this thing. And this is basically going to print a character to the Uart, right? So really, there's kind of two phases of this putC program. Okay, so the first phase is where we're going to check to see if the Uart is available to actually send a character. Okay. One of the problems that we have, of course, is that the Uart is very slow compared to the processor. So every time we send a character, we're going to have to wait a kind of a long time for that character to actually be transmitted out the Uart. and go to the get sent to the remote computer. Okay, so while we're waiting, we need to check to see if the UART is able to accept another character. And basically, we're going to do that by looking at the status register of the UART SRA. Okay, and there's this one bit inside of SRA called the TX ready bit, right? So if TX ready is a 1, that means that the UART is ready to accept a new byte to be transmitted out, right? If TX ready is a 0, then we're not allowed, it's still in the process of sending the last byte that we asked it to send, and we can't give it another byte, okay? So we need to wait until the TX ready bit of our UART is a 1 before we actually transmit anything. Okay, so let's do that. So we're going to make a loop here. We'll call it putc loop. At the beginning of putc loop, we're going to get the address of the SRA. I think it's called S. Let me just check my nomenclature up here. Uart SRA. There we go. So we're going to get the address of the SRA into A0. And then we're going to get the value of that address every time on this loop. Right? We're going to remove 1 byte from A0, which is going to be the contents of our SRA register, into D0. Okay? And then we're going to AND that value with a number that has a 1 in the TX ready position bit 2. So this number is going to be 100 in binary, which is 4 in decimal and 4 in hex. So we're going to AND it with 4. Okay. And if the result of this AND is a 0, that means that this TX ready bit was a 0, and the transmitter is not ready yet. We need to keep waiting. So if so we're going to say branch if equal, which means branch if the last operation resulted in a 0 to our putc loop. Okay, so this tight loop is basically going to continually read the value of the SRA register on our UART, check to see if there's a 1 in the TX ready bit, and if that bit is not set, if that bit is a 0, it's going to go back to the putc loop and check again. Okay, so it's a pretty inefficient way of sending characters, of course, because most of the time we're going to be sitting here spinning in this loop waiting for that bit to become a 1. Okay, now if that bit is a 1, then this AND operation is going to result in a non-zero value, right? And then this branch will not be taken back to the putc loop, and it'll fall through to the next instruction, in which case we can actually send a character. Okay, so what we're going to do to send a character is we're going to put the transmit holding register. Maybe I should go back to my data sheet here and explain this. We have the transmit holding register, which is basically the register that when we write to this register, whatever gets written to this register will then eventually get sent out the UART. Okay, so we want to, once we determine that the transmitter is ready to operate, we're going to write 1 byte to this register, and that byte will get written out to the UART, and it'll get sent to the remote machine. Okay, so we're going to put the address of the transmit holding register into A0, and then we will write our byte out. Okay, so what byte should we actually write, right? We have to figure out how we're actually going to pass information to this function, right? So let me just comment that real quick, and I'll explain how we're going to figure that out. Okay, so we're going to write this byte, and then after we're done writing this byte, then we're going to return. Okay, so the question is, how should we send information to this function putc? Okay, so there's kind of 2 different ways to do this, right? So the first way we could send information to putc is we could put the data that we want to send in one of the registers, and then we could assume that when we get to put C, say register D1 would contain, always has to contain the byte that needs to get transmitted. So that would be the first way we could do it, right? So the first way we could we could pass data to this function would be passing data in the registers. For example, D1 in this case, right? The second way we can do it is we could pass the data on the stack, right? So we can talk about the second way later, but basically the way that would work is that we will push the value, the caller, before we actually call this function putC, the caller will push the value of the data that it wants to send onto the stack, and then putC can get that data off of the stack. Okay, this is a little bit more complicated, but this is sort of like the preferred way of doing it on the 68K processor. Okay, most modern processors like ARM and RISC-V and stuff like that, they usually use the passing data in the registers method because it's a little bit faster. Okay, you don't have to worry about doing memory operations. Memory operations are slow. Okay, so we could put the data in the registers, or we could put it on the stack. Okay, so let's say we're assuming when we get to this function here that the data that we want to send to our Uart is going to be in register D1. So we will write that byte that's in D1 into the transmit holding register A, and then we'll be done, right? Okay. Okay. So now to call this function, what are we going to do? I will put a loop here. Okay, so I'm going to put the value, ASCII value for character A into register D1, and then I'm going to call putC, and then I'm going to branch back to the main loop, right? So what this is going to do, let's assemble this thing first to make sure I didn't make any mistakes. Uh-oh, looks like this program might have frozen. Yeah, I think I'm going to have to restart it here. Let me see, hopefully I didn't lose. It looks like I lost my putC. Okay, I'll have to rewrite putC. Okay, my program just froze here. I had to restart it, and I lost a little bit of my work. I had to retype in the putC function, but it looks like I don't have any errors or warnings. So let me just go right ahead and test this program out. So I guess I also need to call my putC function here. Let's see here. Okay, this looks good. This looks good. So I also have to call my Okay, so here's my main loop. Actually, after I've initialized my 68681, I'm going to put the ASCII code for the character A into D1. So watch D1 as I step over this instruction. Now D1 contains the ASCII code for 1, which codes for A. And now I'm going to jump into putC. Okay. So now putC is going to put the address of the status register into A0. So let's do that. Watch A0 here. Okay, this is the status register, 100,001. And then it's going to continue to loop around, and it's going to get a byte out of the status register into D0. So we just read the value CC from the status register. We're going to AND that with 4. And what you can see is that 4 is the bit 3, which codes for the number 4, is set. Right? So we're not going, so that means that the transmitter is in fact ready to send a byte. So we're going to now, we're not going to take this branch back up here. We're going to go down and we're going to fall through. We're going to get the address of the transmit holding register and address in A0. And then we're going to take the value in D1, which is our character A, and we're going to write it to the transmit holding register. And then we're going to go back. And we're going to go all over again in this loop. So this is just going to simply write the character A to the terminal repetitively. So we can program this. Program onto our Uart and see what it does.